From the University of Tennessee. So he will present joint work with Clayton Dexter, who unfortunately couldn't make it to this conference. And Nick will talk about joint-sparse approximation for high-dimensional parameterized. So we're looking forward to it.
Yes, thank you very much for the opportunity to come and give a talk. Like Claudia said, this is to work with my collaborator, Hoang Tran, and my advisor, Clayton Webster. This sort of began about 2 years ago after some discussions at SIMUQ in 2016. And the idea was that we wanted to do Hilbert-valued recovery via compressed sensing, but there really wasn't a theory for that at the time. So we started from the assumption that we were going to prove things in terms of doing recovery of a Hilbert-valued vector. And what it turned out was that this is actually very closely related to the problem of joint sparsity, and you can kind of think of the joint-sparse recovery problem as an instance of Hilbert-valued recovery. So this talk is to motivate Hilbert-valued recovery via joint sparsity and provide links between these two problems, and then also talk a little bit about how you might want to go ahead and solve these types of problems and what types of algorithms you might want to use. Okay, this is a bit silly. I know this. I always put this at the beginning of my slides to motivate why we care about sparsity. So here, this is what we typically do in imaging. We have we want to represent an image by an expansion in terms of some wavelet basis. Here I've taken an image of my dog on a dock in Tennessee, and I've computed a biorthogonal wavelet transform, and I've set 99% of the coefficients in this transform to 0, so that only 1% of the coefficients remain. And here, on the right-hand side, I've plotted that resulting image. I wanted to zoom in a little bit so I could show just what's happening with this image. So if I look at like the details on the right side of the image where there's some leaves on this tree, and then I look over at the sparsified version of that, you can see that a lot of detail is lost at the finer scales. Nonetheless, it still provides a pretty good approximation in the energy sense, because if I plot or if I compute the energy norm of the error between these two images, it still preserves about 99.63% of the error, or of the energy. Of course, I can keep doing this, and I can go further and further, and I'll lose more and more detail at the finer scales. Here I only have 0.25% of the coefficients remaining, but it still preserves about 99.23% of the energy. And if I keep going to 0.05, now you're starting to see some real degradation in the image, but it's still preserving a lot of the energy of the image. And finally, just as I think this is the last one, yeah. If I go down to 0.02% of the coefficients, I can still get a pretty good energy approximation of the image, but now I'd be questionable if you could even tell that this was a dog on a dock. But the takeaway is that sparse approximations can often provide good solutions, or at least interesting solutions, to real problems of interest. And what we want to do is we want to take this idea and we want to do full recovery of solutions to parameterized problems in the setting that we're typically interested in parameterized PDEs. Okay, so this is an outline of my talk. I'm going to first go into, that was an introduction, I'm going to go into joint-sparse recovery, the problem setting that we're talking about, how we enforce the joint sparsity via regularization, and types of methods or algorithms that we can use to solve this problem. Then I'll talk about parameterized PDE models a little bit, talk about polynomial subspaces and truncation errors, sparsity and best S term approximation a little bit, and then I'm going to give a relation of these two problems. So I'm going to talk about how we can use joint-sparse recovery to solve this type of problem, and then what kind of recovery guarantees you can get, and finally some numerical examples and concluding remarks. Okay, so the joint-sparse recovery problem is simply stated to simultaneously reconstruct a set of sparse vectors. I'll call the set, the set is a set of vectors C, R, indexed by R in some set omega. The key assumption is that they have common support, so that the indices that correspond to the non-zero elements of the vectors are going to be common among all of the vectors in the set. Here, omega can be countable, possibly infinite set. A is a predefined sampling matrix. UR are my measurement vectors. These ER vectors are unknown noise vectors, and the CR are the signal vectors I want to recover. I was thinking a little bit about the theme of this workshop, UQ, for inverse problems, and it seems to me this is somewhat reversed. I want to solve an inverse problem to get an approximation to a UQ problem, because I don't know the support of these vectors a priori, and I also don't know what the noise is, noise level. I can group these vectors into matrices by taking, in each index, I'll just take the vector and I'll put it in a column in a matrix. And this matrix will be in Cm by omega, so it'll have m rows and omega, well, the cardinality of omega columns. And then the problem becomes to solve this matrix problem, U equals AC plus E, for a signal matrix C. And again, the key that we're going to take advantage of, the joint sparsity, is that the sparsity and common support imply that most of the rows of this matrix C that I want the signal matrix are 0. Okay, so how do we regularize this problem? How do we solve it via convex regularization? Well, I'm going to consider this minimization problem of a sum of two functionals here. This is a non-differentiable functional, and this is a differentiable functional. I'm going to define this matrix norm, the PQ norm, as the LQ sum of the P norms of the rows of my matrix Z. What that means in particular is that if I look at the L2-1 sum, that's the L1 sum of the L2 norms of the rows. And this term, the first term here, is going to promote the sparsity in the rows. My second term is going to promote the data fidelity. Mu is going to be a penalty parameter that will be chosen depending on estimates of this noise. And of course, this space, Cn by omega, with this norm, the 2-2 norm, is a Hilbert space equivalent to the space little L2 of C, tensorized to the nth power, with the standard direct sum norm when the rows are assumed to be L2 summable. Okay, so very quickly, I just want to go over the algorithms that we'd consider using to solve this problem. In particular, we focused on Bregman iterations and forward-backward iterations. Specifically, the Bregman iterative algorithm involves iteratively updating the right-hand side, adding in the kth residual at the k plus 1th step, and then solving this problem, a subproblem here, with the different data. The reason that we chose to use this algorithm is because it possesses some nice error-forgetting properties. In particular, I can solve these subproblems with a lot less accuracy and still get a good result after the end of the Bregman iterations. We also focused on forward-backward iterations, which might seem like the natural approach when you have a non-differentiable and a differentiable part of an objective function. And specifically, you can write the forward-backward iterations as a fixed-point algorithm with these two operators are called j tau and g tau, where g tau is nothing more than a gradient descent step, and j tau is row-wise soft thresholding. Recently, we put out a paper in 2017 that establishes strong convergence of this algorithm in the infinite dimensional setting. If you're interested, you can find it on the archive. Okay, so that's all I'll say about algorithms for now. I'll come back to it a little bit later in the talk. But this is the typical setting of parameterized PDE models. So here we have some parameters, y and gamma, subset of Rd, where d is finite but could potentially be very large. We have a PDE model that depends on maybe some data A and the parameters y, and in a physical space, d is a subset of Rn, and n equals 1, 2, or 3. And we want to compute some quantity of interest, q of u, that depends on y as well. As Professor Schwab said on Monday, this is the typical fruit fly problem that we look at, stochastic elliptic problem on d cross gamma. A here is going to be a random field, f is an L2, and my parameters I'll assume for this talk are uniform IID bounded random variables, but they don't necessarily need to be bounded, and we can talk about some strategies in the unbounded case as well. But the goal here is to approximate the solution map y maps to u of y globally in D be an expansion of this form, where I have this vector C, C1 to Cn, is actually a vector of Hilbert-valued functions in the space V, which in the case of the stochastic elliptic problem would be H01. And we're going to expand within an orthonormal basis, or we could also look at interpolating polynomials, but for this talk we'll just focus on the orthonormal basis case. Okay, so of course the first step is to truncate the infinite expansion. We have to choose some set lambda on which to do that. And some common ones that people look at often are tensor products, total degree, hyperbolic cross, Smolyak sets. And of course you can also introduce anisotropic versions of these if you know that you have some particular anisotropy in the problem that you want to capture. But each choice introduces a truncation error, which I'll call eta sub lambda naught, which is nothing more than the neglected coefficients in this sum. Of course, the algorithm costs scale poorly with dimension, because for all of these approaches, or all of these index sets, the cardinality grows quickly with the dimension, exponentially in dimension. And the optimal choice would be to choose the S most effective indices to minimize this error, but that could be unknown in general. Okay, so when can we hope that the solution to these problems is actually sparse or compressible so that we might actually successfully apply compressive sensing techniques to solve these problems? Well, assuming some very common assumptions in the parameterized PDE community, that is coercivity and continuity of the coefficient A and holomorphic parameter dependence, we can show that, and in fact, Professor DeVore's previous paper shows that you can get an algebraic dimension-independent rate of the form of the sum of these coefficients in LP, s to the minus r, where r is 1/2 minus 1 over p, and p depends on the summability of these coefficients in energy norms, and such that r is greater than or equal to 1/2. On the other hand, if I just look at taking the largest bounds, so let's say I have some bounds on my coefficients of the form rho to the minus j, and I want to take the largest of these, then I'll define that to be a quasi-optimal S-term approximation, and that would satisfy an error rate that looks something like this: S times e to the minus 2 kappa S to the 1 over d. This power here of 1 over d is also typically referred to as another contributing factor of the curse of dimensionality, because it shows up explicitly in the convergence rate of these approximations. And here kappa also depends on the size and shape of this quasi-optimal index set lambda s, I'll call quasi-optimal, and rho is dependent on the region of analyticity of my coefficient A. So I'm just citing these results, but we ended up using them, or we will end up using them in the forthcoming paper when we prove some convergence rates for these types of approximations with joint sparsity. In practice, though, if I actually take a real coefficient, so let's say I take the log transformed KL example, and I look at an 11-dimensional problem with a correlation length of 1 over 64, and I plot the energy norms with respect to multi-index, and then I sort them by magnitude, then I do see that if I want to get down to, let's say, 10 to the minus 3 error, I only need about the first 50 or so coefficients in a basis of size 300. So it is possible for some realistic problems, or at least for some of the fruit fly problems we typically look at, to get sparse approximations that might satisfy error properties we want. On the other hand, if I look at pointwise error decay, and this is what really kind of motivated our joint sparse approximation technique, it's not always obvious, to me at least, what the magnitude of the coefficients are, what type of errors to use when parameterizing the solvers. Because in honesty, you need to have some kind of an a priori guess on the error, the truncation error, in order to parameterize the solver. And so it seems to me, at least, if you want to do functional recovery pointwise on some grid, this might present a real challenge. And that's unfortunately what I've seen a lot of, is standard applications of compressed sensing to pointwise functional recovery at points in a finite element discretization. I've only seen a couple of examples where people have done this on all the points of a discretization, but what's interesting is that the numerical results later will show that you can obtain a better result by doing this global approximation strategy than the pointwise recovery approach. Okay, so if I wanted to actually solve this, I might consider this problem, I might consider to look for a sparse approximation. I might consider a V-norm regularization of similar to the joint sparse convex regularization I looked at earlier. And what would that be? That would be basically I'd replace the 2 norm on the inside of this sum with the V norm associated with the Hilbert space of my solution family of PD. If you know that the Hilbert space excuse me, V is separable, i.e. possesses a countable orthonormal basis, then we can write each component of the solution vector C, C1 to Cn and Vn, in this sum, in this expansion. And if I group these coefficients into a matrix, I'll call it C hat again, in Cn by omega, then we have this equivalence of norms. So I have the VQ norm, which is the sum from j equals 1 to n, the V norms of the jth component of this vector, to the power q, 1 over q. And this is equivalent to this sum through Parseval's identity because I have an orthonormal basis, which is nothing more than an L2 sum of some row of this matrix. So I have that this is equivalent to the 2q norm of this matrix. So we can think of the solutions C and Vn to this problem too as a matrix C hat and Cn by omega. One of the details I haven't really mentioned though in previous versions of this talk is that when we typically do this is we apply a finite element discretization. And when you apply a finite element discretization, you don't exactly have the equivalence of these two norms, so the problem is slightly different from standard joint sparse recovery. Nonetheless, we can still solve the V-norm regularized problem by modifying the solvers to compute these V-norms when necessary. And then this desired solution is still a row sparse matrix. I'll call it C hat and Cn by K sub h, where Kh is the dimension of a finite element space. Or you could also still think about this as a sparse vector in this tensorization of finite element spaces. Okay, so quickly just to go back to those algorithms, this is how you solve the standard joint sparse recovery problem. If I wanted to modify these solvers to solve the V-norm regularized problem, all I would need to do is everywhere you see a 2 norm is replace that with a V-norm. So here and here I would replace this with the V-norm. Here and here I'd replace those with the V-norm. And I'd be solving a bunch of subproblems of energy norm regularized convex minimization problems. How can you actually set up this problem to solve, how can you set up the measurement scheme from the first couple of slides to solve the joint sparse recovery problem and an approximate solution of parameterized PDEs? Well, the answer comes from structured random matrices from compressed sensing for polynomial approximation. And there you need the ingredients of a multi-index set, random samples drawn from some measure, the measure associated with your probability distribution, and these would be just standard Monte Carlo samples. And then you need a bounded orthonormal system, and you'd set the matrix, your measurement matrix Aij, in the jth column is going to be the basis function psi j, evaluated at all the points yi. And then you'd set your data to be a matrix of the sample values of your parameterized PDE solutions at the points yi. Okay, so what about recovery guarantees? Specifically, when I talk about recovery guarantees, I mean with respect to the number of samples that is required of the PDE solution in order to get an approximation. So in compressed sensing and also in joint sparse recovery, we have this uniform recovery is guaranteed by the restricted isometry property of the normalized matrix A tilde. And this is really what we got started with, is thinking about how can we modify the RIP to do this Hilbert valued approximation. And so the natural thing for us was to think about reformulating the RIP with respect to these V2 norms. And then it's really easy to show actually that a matrix A tilde will satisfy the standard RIP with delta S if and only if it satisfies this VRIP property with the exact same delta S constant. What this implies, of course, is that means that query complexity for complex valued signal recovery carries over to this case. So that means that if I have a bound like this, a lower bound on my samples, then with high probability A tilde will satisfy this VRIP with the same delta S. Okay, so I think I just have enough time to go into some numerical examples, and then I'll finish up. So let's return back to the stochastic elliptic problem. We'll specifically focus on a known KL expansion of a random field associated with a squared exponential covariance kernel. I'll choose some correlation lengths, and I'll play around with the dimension a little bit to see what happens when we try to do sparse approximation in high dimensions. The setup for our problem, how we're actually going to run these experiments, is we're going to fix a total degree subspace lambda naught with n large, isotropic, and we're going to increase the samples according to this rule. So I'll take k through 1 through 7, and I'll multiply k times n over 8. So I'm looking at various ratios of the cardinality of my subspace that I'm approximating in. I'm going to solve this with Bregman iterations, forward backward splitting. And because like I said earlier, you need an estimate of the tail error in order to actually use these solvers. What we're going to do is we're going to compute an estimate of the tail error eta lambda naught using the stochastic Galerkin method. And then I'm going to use 1.2 times that as a tolerance for the solvers. So I'm shooting within 20% of the actual tail error of the approximation. And then we're going to average this over 24 trials. So the sample points and the subspaces will be fixed for both the compressed sensing method, also the stochastic Galerkin method, and this joint sparse approach. what we're going to do is we're going to solve using what we call the decoupled approach, solve the same problem with compressed sensing pointwise for a functional of the solution at the point evaluation functional. And then we're going to also solve it with stochastic Galerkin, total degree subspace of order p equals 2 and 3, stochastic collocation with Crenshaw-Curtis points in the doubling level, our doubling rule, L equals 2 and 3, and then Monte Carlo method with uniform sampling. So in all of the random sampling methods, we're going to use the exact same samples, but what we're really trying to do is use those samples more efficiently with the joint-sparse approach. Okay, so if I compare the decoupled and coupled methods, or the joint-sparse approximation, what was really interesting to me when I first saw these plots is how different the approximation errors are between them. In fact, it looks like in every case here, it's almost an order of magnitude, at least, difference between these two approximations. And there's a couple of reasons I think that this is true and is happening in this problem. First of all, again, I don't know the pointwise truncation error associated with my PD when I choose a polynomial subspace. So it's hard for me to actually get an estimate of what tolerance I should use for the solvers for the decoupled approach. On the other hand, when I solve the joint-sparse approximation, I know that my error for the solution of that problem will scale like the L1 norm of the best S terms and V norm of the true solution, and so plus also another constant with the tail error. So I think what's going on here in particular is that it's a combination of both. I'm unable to solve the pointwise approximation problems at the same tolerance as I can solve the global approximation problem with the joint-sparse method. Of course, this is a 100-dimensional example, highly anisotropic, and a very high order, or very low order, but high cardinality subspace. My finite element mesh here is about 206 degrees of freedom. And the plots on the right, in particular, just show that this would be the type of problem that I would want to apply these sparse approximation techniques, because if I need to get ordered machine epsilon, I need about 100 of these coefficients. And so that's really sparse compared to a basis about 5,000. Okay, so this plot is the first of a series of plots in which I increase the dimension from 20, going up about, I think, by 20 each time. I keep fixed the correlation length. The cardinality of this subspace will grow, of course, because it depends on the dimension, and the cardinality of my finite element approximation is going to be fixed. For the stochastic Galerkin method, the degrees of freedom corresponds to the cardinality of this subspace that I'm using. It's the number of samples for all other methods on this plot. And I think this is at least an acceptable comparison because I'm looking at a linear KL expansion problem in which the complexity of solving the Galerkin system is approximately linear. And so here I've plotted, again, these things with respect to stochastic degrees of freedom. And like I said, what we're really trying to highlight here is that as I increase the dimension, the relative sparsity S over N is decreasing. And I'll get a better and better approximation. So when I go to 40-dimensional problem, N is 861. When I go to 60-dimensional problem, N is 1891. Remember, I'm growing the number of samples proportional to the cardinality of my subspace. And finally, in a 100-dimensional problem, N is 5151. The left-hand plot is the relative error in H01 of the expectation. This plot only uses the first mode of the solution. The right-hand plot is the relative error in H01 of the standard deviation. It uses all of the modes of the solution. And so I think in high dimensions, the reason that we're able to see this error is because, again, I'm using the subspace associated with this plot right here, this data point for the Galerkin method, the same subspace for the joint-sparse method. And so I'm getting within an order of magnitude, or within the order of magnitude of that approximation, but not quite reaching it. And then finally, our final example on the linear problem, here I've increased the correlation length to 1/2, same basis, same dimension, and now I actually see some stagnation, I would say, maybe about 20% stagnation corresponding to the tolerance that I use for the solvers for the joint-sparse method. I'm sorry, this has the wrong label. It should say JSMTD. Okay, this one is a plot of a nonlinear parameterization, the log transform KL expansion in 17 dimensions. Unfortunately, I'm unable to give a comparison with the stochastic Galerkin system because I can't solve this problem with my solver. That could just be due to implementation errors. Maybe there's a more efficient way of implementing this, but I simply couldn't actually solve that problem with the Galerkin method. So this is 17 dimensions, and I chose a correlation length of 1/8 in this problem, and I bumped up the order of the total degree subspace to 5900 and order 4 with 5985 basis elements. I also bumped up the number of degrees of freedom on my mesh to approximate h to be about 1/32. And what was really interesting to me for this plot is now this joint-sparse method is doing, it seems better than collocation even with respect to the number of samples that I needed, even in the expectation, which again only uses the first mode of the solution. But it also does better with respect to the standard deviation. Okay, so with that I'd like to conclude. We've discussed the joint-sparse recovery problem. I still think, I didn't get to talk much about this because I have a whole other talk that's about an hour long that goes through convergence theory for forward-backward splitting. And we recently showed, again I say, the strong convergence of that method. I'd like to show similar strong convergence for the Bregman iterations. I'm not 100% confident I can do it yet, but I'll keep trying. And we've also showed a connection between the joint-sparse recovery problem and parameterized PDE problems. I still think we need more numerical experiments, in particular for nonlinear parameterized PDEs, and also linear versus nonlinear stochastic parameterizations. Here's an incomplete list of references discussed in this talk. And with that, I'll conclude.
So you're trying to find a forward solver.
Yeah.
And with a reduced model of some sort.
Yes. It's a sparsity assumption.
Yeah.
So,
well, where is the sparsity assumption occurring? On the diffusion coefficient or on the solution?
it would be in both. It would be a natural consequence of the diffusion coefficient having a
Okay, so
sparsity.
you start with the diffusion and you conclude that you get sparsity in the solution. Now, the usual problem we have in these reduced models is the offline finding this good reduced model.
Yeah, yeah.
And
I think I know where
I
you're going.
didn't see
Comparison in
how
terms
that
of
was addressed here.
No, so that's a future work, unfortunately. I think that'll require a lot more study. So what we're trying to really play here is the balance between solving the PDE problems at the samples versus solving this convex optimization problem. And this is a dense convex optimization problem. All the matrices involved are dense matrices. I think the order of the complexity for the algorithms I'm looking at, for these algorithms at least, is like n squared times k, where k is the cardinality of my finite element approximation. And so at least it's linear with respect to the degrees of freedom in the physical discretization, but it's, I think, quadratic with respect to the cardinality of the subspace I'm approximating in. On the other hand, though, I can sample this PDE at a bunch of random samples. Those are independent of the optimization procedure, and I can change the subspace after the fact. So if I've identified approximately the support of the best test terms, I can then contain that and grow the subspace even larger to find even more terms and throw away the terms that were not so important.
So another thing I didn't catch was you know, when you look at solvers for finding sparse solutions, typically you assume that you have an RIP matrix.
Yeah.
You're assuming that, but is that something you prove about that the matrix occurring from your?
Yeah. So the structured random matrix associated with the polynomial basis that we're
high probability.
Yeah. That's one of our previous papers on polynomial approximation. It's the lower set paper with Della.
Okay, now my last question, probably not too many people want to ask questions, but my last question has to do with how many iterations of Bregman. See, in other solvers, like if you use OMP or something like that, we have explicit guarantees that only so many iterations are necessary to recover. Do you have that in Bregman?
Well, I think you have an explicit bound on the error. So we have a monotonic decrease in the error, which you can explicitly bound with respect to the number of iterations, and that's something I've already proved. It follows directly from Osher's results. Actually, it's kind of silly that it just does, but it does.
I thought in Osher's stuff, he never said how many iterations he has to.
It's not.
It's like
So actually, they prove in the finite dimensional setting, they prove finite convergence. So for that's just for the standard L1 minimization problem. They also prove that you can get an explicit representation or an explicit bound in terms of k, the number of iterations on the residual of the problem. But so far, I've been able to prove that part, but I haven't been able to prove finite convergence or even convergence of the algorithm. All I can do is go back to his papers on total variation and prove this essentially existence of weak star convergent subsequences, which is not satisfactory. But yeah, that's where we are right now with that. In practice, I see that it requires approximately 10 to 20 iterations of Bregman, and maybe per each one of those iterations, a couple hundred of FPC. Fixed point continuation, which is forward-backward splitting with the continuation strategy on the step size of the forward-backward iterations.
Okay, thank you. Any further questions? No, this is not the case, so thank you once again.